Okay, so whenever you're ready.
All right. Hello, everybody again. Thank you for coming again. It's nice to see the usual people's names here. And there's my brother walking. Excellent. So today, when they asked me to put these talks together, I just banged down a few topics. And the topic for today is these generative adversarial networks, because I think that they were cool. But when I went to look over the slides I have for them, I don't have enough material to fill today, and so I've just stuck in all the various topics that I know about machine learning that we haven't covered yet, and we'll just keep doing them until we run out of time. So first off, let's see. First off, I want to restate something that Martin and I talked about during the reinforcement talk. And I said something, somebody asked the question during the dimension reduction talk, and I gave the wrong answer. So I want to give a correction to that too. So in terms of the reinforcement talk, remember we update the R value of the various nodes, and then we had a discussion at the end about what order to put to update the nodes. And the truth is, I'm making this up, but it's a pretty good guess. Is that if AlphaGo was learning from watching humans play, then they have lots and lots of games that humans have played. And so they know what the end game is supposed to look like. And so they'll just start back there, right? They know the R values for those, for the end one, because that's the end of the game, and they can evaluate who's winning. And then they can backtrack. And it's just like the a tree of game tree, unless here's this example had a little cycle in it, so you could go around the cycle. But I think that's pretty straightforward. If the machine is trying to learn by itself and doesn't have any access to games that have been played before, then it has to do stuff on its own. And somewhere in psychology, I learned that if you flash up the board, a chess board or a Go board, I suppose, that comes from a game, then the experts will understand it really quickly, right? But if you flash up something that doesn't come from a game, then people don't understand it. So that's what we're going to. We don't expect our machine to understand every layout of a board, only those that are likely to come from games. So, and the problem is, before we start, the machine doesn't know what an end game looks like, right? And there are just too many board placements. So what I'm suggesting is you start off with random, the machine doesn't know anything. So when it plays its first game with itself, it's kind of random, and then it backtracks and learns based on how well it did in that game. And then it'll try another game and go backwards, and then it'll try another game and go backwards. And I think if it keeps doing that, it will eventually converge on games in which everybody is playing optimally, and that's how I think AlphaGo learns to win. Does that make sense, Martin? That's what we were kind of talking about before, right? Here's the other thought when we were doing dimension reduction, right? We have all this data, which were faces, and we projected them down onto a lower dimension. And we did, and people were kind of confused about this spot versus this point, right? This point here is placed in a 10,000 dimensional vector space. So it's telling you the brightness of each of your 10,000 pixels, right? So if it's a point located, it tells you how bright this pixel is, how bright that pixel is. And so in the end, if you know the brightness of all 10,000 pixels, then that gives you an image, right? And then when you project it down to this point, well, now it's in a 100-dimensional subspace. So if you can tell where it is along this dimension and this dimension, then it requires fewer numbers. But you'll see it's still located within our 10,000 dimensional space. And as such, it tells you the brightness of every pixel. And so you can still get an image out of it. Now, the bug that I talked about, remember, is we collected all this data. We expected value in the covariance matrix. And then at the end, somebody asked, how much data do we need in order to collect all this information, right? How many images? And what I answered, just kind of off the top of my head, is, well, it seems like you got 10,000 dimensions, and your 10,000 dimensional vector space is going to be pretty empty unless you have at least 10,000 images. Or maybe even if you want to fill the whole space with 2 in each dimension, then you need 2 to the 10,000, right? Which is a lot of images. And it occurred to me after the fact that no, you don't need nearly that many images, right? And remember when we covered this when we were doing the talk on how do you generalize to other data, right? So remember we talked about how much data do you need in order to be able to, how much training data do you need in order to be generalized into new data? And so let's just crank out the math here. Suppose you randomly choose some D images. And as you might remember, we talked about standard deviations. If you flip a coin n times, then the standard deviation is the square root of n out of n flips, right? But if we scale our sum down so that it's, we divide it by d so that it's a number out of 1, then the standard deviation is 1 over the square root of d. And you might remember then we said, well, what's the probability that you deviate more than c standard deviations away? Well, you get this nice little equation. And then we talked about the union bound, where if here I have n squared numbers that right, all of my covariances that I'm trying to learn. And each of those numbers, if I'm choosing my data randomly, right, it's not likely to deviate by more than this with this probability. So what's the probability none of my n squared values deviate by very much? Well, you take this probability and multiply it by n squared. All right, to give you a probability that nothing, right? This is the probability that something deviates, right? And if we want this much deviation, right, C deviations to be less than 1%, right? We want all our numbers here to be within 1% accuracy. Then we need this to be less than 1%, which you can then solve for D. And we want the probability of failure to be small. So that can give you how big D is. And you see here, D is just order log n, which is much better than n or n 2 to the n. Anyway, I went kind of fast there because it was sort of slipped in from previous talks. So, I'm not sure this really belongs here, but supervised learning is, remember when you have the supervisor is telling you labels. And what is unsupervised learning is when you don't have a supervisor telling you any information. And here's an open problem that machine learning people haven't managed very well. So you could get a machine, right? An alien. Suppose an alien is your machine, and the alien arrives down to Earth and looks around. And what is she going to figure out? She's going to figure out there's objects that look like this that move around, and they stop moving when they come up to objects look like this, right? So the machine would learn those various things. Of course, she wouldn't be able to say that was a car or that is a stop sign without some sort of supervisor telling her the labels of these things. But a non-supervised person should be able to say, hey, this is some object that travels around a lot, right? Does that make sense? All right, so we are going to do something that I think is kind of fun here. And let me try to breathe and slow down a little bit because I might be losing. Anybody have any thoughts so far? Questions about anything from the past? All right, so here, suppose that we don't have a supervisor telling us anything, all right? What can we learn? Well, let's say the world, we're assuming that the world is some distribution on images, right? So it could send us random images. We ask for a random image, it gives us random images according to some distribution. And what we were doing before is we were trying to label, identify, is that a face or is that a bicycle, right? And the problem is that now we have no supervisor to tell us which are which. So there's no way we can answer that question, right? There's no answers without a supervisor. In fact, without a supervisor, there's not really even a question, right? Since all we have is this data, these images streaming at us, nobody's giving us answers or questions. All right, so here's a fun thing we might try to do. Let's try to pretend that we have, what we have coming in to us is just random bits, right? So here's just streams of random bits are coming at us. And what do we want to do with those random bits? We want to pass those random bits through some neural network that we're going to build, right? We're going to learn this neural network. And what it's going to do is when you give it random bits, it's going to output an image. And where does it learn what image to output? Well, what it wants to do is it wants that when it's given a random bit strings, these are just random coin flips, it wants to output an image that looks like the distribution that it's watching, right? So its goal is to learn this distribution of images, and it learns it so that when it's given random bits, it outputs something that looks like a random image, right? So it's given different random bits and it outputs different images, right? Now, how is it going to learn? All right, this is really quite a fun little thing here. We're gonna simultaneously have two players, two machine learning, right? Remember this top machine, he's trying to learn to pretend to be the distribution, right? And the bottom machine, her goal is to distinguish between what is a random image and an image given to us by this faking rand distribution, right? So by the mimicker, right? So this is a mimicker who's trying to generate random images. And this machine down here's goal is when it's given an image, needs to tell you whether it was produced by the random distribution, the true random distribution, or by the mimicker. So let me give you an example. Suppose some random bits come here, which gives us the mimicker, then comes up with some image that we feed into the distinguisher. And the distinguisher is what's the correct answer for the distinguisher is to say that image you just gave me came from the distinguisher, right? On the other hand, and now you might say, well, who's going to tell her whether she's right or wrong? Well, who's ever feeding them back and forth knows, right? So it's kind of the supervisor knows where this image came from, and this supervisor who all just knows where these images comes from can tell the distinguisher whether she was right or not. All right, so that acts as our supervisor, right? And so you get a right or wrong answer. You do gradient descent to feed back the error through this machine so the machine can learn, right? So let's do another example. You know, this image actually came from a random image from our true distribution. So what the machine needs to say, the distinguisher needs to tell you that it came from the true random distribution, right? And so again, the supervisor says right. Right now, this is a strange image that came from the true distribution. So maybe our distinguisher will get the answer wrong. You know, the distinguisher will say, hey, I think that's not a true image. Come on, what are all those bananas doing there? And then the supervisor will say wrong, and will feed back the error through here and update the weights. Right? Is everybody kind of following that? Right? Now, what's going to happen when we do this? Right? So, so the discerner is rewarded for getting the correct answer, for just discerning correctly, right? And what is the mimicker rewarded for? Right? We also have to feed back right and wrong answers. You know, if the supervisor tells the mimicker she's right or wrong, we got to feed back the error. But what is the error? Is the mimicker is rewarded if he can fool the discerner, right? Whenever, so anytime he gives an image, he's told whether or not he was able to fool the discerner. And if he doesn't fool, then that's an error, and it goes back, and that error trickles back and changes the weights as if we had a supervisor, right? So the mimicker is going to change his weights based on in order to fool the discerner, and the discerner is going to change her weights in order to learn how to discern, right? And what's going to happen? Well, we start off with random weights. All the weights are random when we start off because we don't know how to do anything. And so when these are random weights, what's going to come over? What is the discerner going to get? When half the time it's going to get what's effectively noise because the mimicker doesn't know how to mimic. And half the time the discerner is going to get images, true images from our distribution. And so it won't take very long for the discerner to learn to distinguish between true images from our distribution and from this random noise that the mimicker is giving, right? So quickly the discerner will learn, right? And as the discerner learns, well, effectively the discerner is learning what the distribution looks like, right? The discerner is learning how the true distribution is different from random noise, right? Now, once the discerner gets good at discerning, right, then the mimicker is going to step in, and the mimicker is going to start learning how to fool the discerner, right? The more the discerner learns to discern, right, the more the discerner needs to understand the true distribution So the mimicker is going to have to learn the true distribution in order to be able to fool the mimicker. Right? Does that make sense? Yeah. So I think it's a pretty cool little thing, and you can see what happens, right? Eventually, the mimicker learns to do a pretty good job at fooling the discerner. So that means, and since the discerner has learned to be pretty smart herself, that means the mimicker is pretty good, and the mimicker is actually outputting things that look like true images, right? Now, does the mimicker always get it right? Right? Here is something that we might not consider to be a true image of a bicycle, right? But the mimicker might output things that aren't truly bicycles or truly images, but things that we've never seen before. The mimicker is going to output things never seen before, and that's kind of cool, right? It's gonna generate new things, all right? And right, so everybody, and that's how without having a supervisor, somehow we get our neural net to learn this distribution of images, right? And what might you do with that? Well, one thing you could do is you could make art, right? So here's an example. Here's a bunch of art, and you can try to figure out yourself which one is made by an artist and which one's made by the mimicker. And it turns out that F is the only one made by the machine. And I really like F.
Me too.
Right? Look at it, has a face here right side up and a face here upside down. I think it's a brilliant piece of art, right? Another thing you can do is you can then ask it, once you have the machine, you can say, hey, somehow, I don't know quite how you get this in, but you can say, hey, give me one piece of art that kind of looks like a texture of another piece of art, right? You can get it to generate cool things. And right there's a cool piece of art. Actually, another fun thing that you can do with these is, since they're determined by random bits, right? You can start with an image, given a bunch of random bits, you can say, what's the image? And then you can slowly change these random bits, right? Just change a few of the bits and see how the image changes as you change a few of the bits. I think that's kind of fun. Any questions about generative adversarial networks? Because that is all I have on the topic, which was today's topic. But if people are still, I'll still keep covering new topics as long as people don't holler. So this isn't neural nets anymore, but another type of machine learning that has certainly been popular through, I don't know, the 70s and the 80s and stuff, was these decision trees. And I'm just mentioning them because they're a classic that people still use. So here are the various, again, we have various X values which define your object. And then given all the X, here's one particular object, and maybe it's this one's labeled red circle and this one's labeled blue square. And our goal is to learn, given a new data item, right, that might not appear here, right? We know when we learn it's all its X values, we want to learn whether we think it's a blue square or not, right? And so what a decision tree is, like playing 20 questions, right? You start at the top and you say, I have a new value, new tuple of X values, and I can ask, is X1 greater than some weight? And if it's greater than, then I go over in this half. And if it's less than, I go over into this half, right? And then I kind of recurse on one half, right? If I'm on this half, Then I ask about x2, right? Is x2, is it bigger than this number or is it smaller than this number, right? Oh, I guess here I got it, right? Oh, I'm coming this way, right? If it's bigger than, if it's yes, then I come this way. And then I query about x2 and I go this way or this way. And if I come to this half, right, then I query here about x1 again to say this or this half. And eventually I get down to being able to say whether it's a square or a circle, right? Does that make sense? And, when you play 20 questions, you have to go all the way down until you know what the object is, right? What is the person thinking of? But here you just have to go down far enough until you give it a label. And I know my son did a project where he was doing random decision trees. Right here, the supervisor gives these labels, right? And what would a random decision tree be is you have your training data, you randomly pick one of the variables, right? And then you split the data, you decide where to split the value, right? Where do you set the threshold for that variable to sort of have as few errors as possible? Somehow you decide where to make that cut. And then you recurse on both sides, right? Then you recurse on that side and you keep recursing. And that gives you a random decision tree. And what he was doing was he was coming up with he had one set of data and he came up with lots of decision trees. And when he was trying to evaluate a new point, he somehow applied the new point to all the decision trees and somehow took the average answer. All right, so when do these decision trees not work very well? Well, you can see if all our questions are asking for values of, orthogonal, right? They're asking about one variable versus another variable. And our separation is somehow along a diagonal. Then you see you're going to have a lot of different leaves in your tree. Anybody, any questions about decision trees? Another topic is another machine learning algorithm, which would be even kind of easier, is suppose we have all this data already and it's labeled by purple means something and orange means something else. And we're not going to do, this is all our supervised training data, and we're not going to do any particular learning ahead of time. What we're going to do is if we're given a brand new point and we want to know what the answer for that point is, what you do is you have some parameter k, and you just in sort of Euclidean distance sort of way, you ask which are the training data which are the k training data values that are as close to me as possible, right? And then, well, the supervisor has given you the answer for all the training data. So you just give that kind of the average answer, or maybe if there are a bunch of different answers, you can say, well, on 80% of these, I think, it's a cat. And on 20%, it was a bicycle, right? All right, so now let's go over to unsupervised learning. So here we have all this data that we want to cluster, but we don't have the colors to help us, right? And somehow we just want to cluster things based on some geography. So how might we do? We want to group together things that are close geometrically without knowing anything about these objects at all, right? Just eyeballing it. You would, suppose you didn't have the colors, right? And you were just eyeballing it. You would probably group this as a group, right? You'd probably group this as a group, right? Because there's white space in between, right? And that's kind of what we're trying to do here, is to cluster things that are close together as opposed to things that have gaps between them, right? And what's funny is, right, this point and this point, they're both purple, Why? Well, because there's this whole string of things in between that are purple. Yet this guy here, right? This one is geometrically, this point is geometrically closer to that point than that point. But why do we make those the same color? Why do we make this one same color as that instead of the same color as that? Well, because there's all the stuff in between, right? That's the thinking. And so we want to, this is kind of I said the alien comes down and is going to say, oh, I'm going to call those something. I don't know what they're called, but I'm going to group them in a cluster, and I'm going to group those in a cluster and these in a cluster. And we won't be able to say that these are cars and faces and bicycles. Why? Because nobody's given them those labels, but hopefully it can cluster them correctly, right? Does that make sense, what we're trying to do? Right? All right, so here is some algorithm I think I learned as an undergrad somewhere, or who knows when I learned it. Somewhere it bumbled into my brain. What we're going to do, by the way, I made fewer clusters. Why? So that my algorithm was clearer when right? I made the clusters more distinct to make it clearer how my example works. All right, so you decide ahead of time how many clusters you want. All right, so we're going to have some K clusters, and I'm going to grab K random points. Those are the black guys, K random points. And then we can partition all of our training data based on which of the K points is it closest to. And these are called Venn diagrams. I forget what these called. These are called something diagrams. There's some name for those. Anyway, you'll in fact, what the red lines are is you see here this dot and this dot. The red lines are the set of all points that are equal distance from this and this, and so it partitions the space into who you're closest to, and of course this has nothing to do with our data yet because we haven't looked at our data at all. And then we look at our data, and for each region here, we just take the average data point, right? So I just eyeballed this. Of all the data that's in this region, that seems to be the middle, right? And these guys are counted and these guys are counted. So I don't know if that's a very good middle. Probably it should have been out here more. I think I moved my middles a few times. So anyway, I was trying to get the average middle, right? And then you repeat, right? Now with our new points, right? We're going to partition the data based on what you're closest to, right? And then you refine, then you remove things, your points to the middle of the data. And the idea is if you keep alternating between those two steps, you'll partition the data. And you'll see how we did a pretty good job in our example. This cluster got cut in half. Why is that? Well, it's because I chose K to be one bigger than the number of clusters that there actually are. And I wasn't sure what that extra K was going to give me. And what it chose to do was to cut that cluster in half. Right? Does that make sense as an algorithm? All right. So let's quickly come over to maybe not so quick. Here, I have another set of slides, which are just various things that people who know about machine learning tend to know. All right. So remember when we're doing hill climbing, you need to decide, you learn that the direction the head is this, but how big of a step do you make, right? If you make really small steps, then your running time's too big. And if you make really big steps, then you might leap over the valley and have a disaster, right? So you need to have sort of a balance between those two. And one thing that comes naturally from the derivative is that it tells you you take a bigger step when it's steeper. And also people tend to have a schedule in which they start with bigger steps and they make their step size smaller as they're hoping to converge in. All right, so that's just kind of what I said. I think I might have said this at one point, right? Here, if you start here and do hill climbing, you land there, right? If you start here, you land here. If you start here, you land here, right? So we're not finding the global minimum. We're only finding sort of a local minimum. And, you know, you might want to start in a number of random places and see where you end up and take the best one, right? But one talk I saw somewhere said that that you think that B is worse than C, right? Because C has a lower error. So you might feel that B is not as good as C. But they were arguing that maybe B was better than C. Why? Because B has a wide basin. And so it might be less, it might be more generous when you have new data come in, right? You want to generalize to new data. In here, right, if you make small changes, well, this is small changes in the weights give you big changes in the error, but it might correspond to having small changes in your input values, giving you bigger error. And so while this might allow for bigger changes in your input data. So anyway, that was just a thought that it's not really clear what we're doing. But here's another thought. When people were first thinking, could we recognize faces this way? They didn't know what the data looked like, what the error surface looked like, right? So if the error surface had, you know, some exponential, lots and lots of little bumps and only one deep valley, right? How would you ever find that deep valley, right? It would take you an exponential time to search all these little local minimums to find this deep valley. And so when Hinton, you know, I guess when I was a graduate student, Hinton was saying that machine learning is going to be great. We just need enough data. And people were sometimes saying, well, maybe not, because maybe this would happen. And what turned out to be the case is that when our data had some pattern to it, like they were pictures of cats, then in fact, you find these really good local minimums. You know, it works really quite well. So that's sort of saying that the data doesn't, right? When you have a nice pattern to your data, like they're images of cats, then the error function doesn't tend to look like this. It tends to look more reasonable, right? Does that make sense?
Jeff, here you talk about how a minimum which isn't actually your lowest minimum might be better because it might be wider.
Right.
But is there any reason to assume that your non-lowest minimum is more wider than your lowest minimum?
Oh, no, absolutely not.
Okay.
No, and I don't have anything more to say about this other than I heard it as one line of something. I think what they were saying is, suppose you ran your hill climbing algorithm many times and you came up with these various solutions, right? These various machines, and now which one do you want to keep?
I see.
Right? Which one treats you better? And you know, there's a lot of grad students trying to write PhDs on something, and I think some PhD somewhere says, hey, maybe those that happen to have a wider basin generalize better.
I see.
Right? Now, what do you do with that information? I don't know. Somebody probably is doing something with that information.
Okay, good. Yeah, that makes sense. Thanks.
All right. So here, I think this is a common thing to do in machine learning, is to add momentum to your hill climbing. All right. So here's right? Here's a ball that's rolling back and forth. I did a Google search for momentum and got that little animation. All right, so here's a long skinny valley. I think about this is a river base, right? It has slopes like this, steep slopes going left to right, but in a slow slope that the river takes to get down to down the river valley, right? The water is flowing at the bottom of this valley, and your goal is to find where the water ends up, way down here, right? And so the red line is saying if you're doing gradient descent, right? If I'm sitting where the arrow is and I say which direction do I head, you'll see I go 90 degrees to the tangent line, to this 90 degrees to this, what do you call it? Contour line. And it's going to take me this way. And I'm going to overstep because I take too big of a step. And so then I say which direction, and I'm going to move back and forth like this, right? Everybody sort of see that that's what's going to happen. And another alternative, what we want to do is we want to do something more graceful. We want to end up like the water does, right? And what does water do, right? We don't want to go back and forth the banks. So what we do is you think about your little guy that's moving, not only having a location, but it's also a little guy has a certain momentum. It's moving. It has a velocity that it's moving in a certain direction, right? So, and you'll see what happens is you move, and then what do you do? How do you change? What does the slope do to you, right? When we're doing the red edge, red line here, what you do is you find the direction of steepest descent and you take a step in that direction, right? But now it's saying, don't do that. Suppose you're standing here and you have a particular, not only am I standing here, but I have a direction that I'm traveling. Then what I do is I have the hill, just like if I was a ball, the hill would change, would accelerate my ball in some direction, right? It doesn't change, the hill doesn't influence my location. My velocity influences my location. What influences my velocity is the hill, right? And so what would happen if you started rolling, you would roll fast down the hill, you would roll up the other side, and then as you roll back and forth, the momentum going this direction and this direction, right, would cancel out. And what you would do is you would slowly build up momentum, velocity, you'd slowly build up velocity down the bottom of the riverbed, and the back and forth would cancel, and you would be moving down the bottom of the riverbed. Does that make sense? Right? People kind of get that? So that's a momentum idea. Here's another thing, which is batch size. All right, so suppose I'm standing here and I have all my training data. So what do? I look at all my training data and I calculate which direction to move. And then I look at all my training data and I decide a direction to move, right? So you keep doing that. And hopefully you're getting tired just watching it, because you every time you look at all the training data to calculate steepest descent and take a step, right? Now that, because we have lots and lots and lots of training data, that is an awful lot of work, right? So looking at all the training data, each step is too much work. So what we're going to do instead is we have a batch size, and we partition our training data into batches. And what you do here, let's say we're starting here at this time, you're starting there. What you do is you look at one of the batches, and based on that batch, you say, how much error is there in on my current machine for this batch of training data? And given that error, I'm going to update my machine by taking a step in the direction of steepest descent, determined just by that training data, right? I'm ignoring all the other training data, and that training data tells me which direction to head. So I take a step, and then I look at the next batch of data, and I determine which direction this batch tells me to go. And then I say, well, which direction does this batch tell me to go, right? And I keep doing that. Every time I want to take a step, I look at a different batch of data. And when I go all through and I've seen all the data once, then I just cycle around and start doing it again through the data again, right? Does that make sense? And why do we do that? Well, I think I've already kind of indicated that. Here I keep going, because it reduces our time, right? Every time you take a step, you're just looking at a fraction of the data. And every time you go through all the data, then that's called an epoch. I don't know why. Isn't there something, dinosaurs have the epoch of this dinosaur or that dinosaur? I think that's the word. But anyway, when you're doing machine learning, you have to tell it how many epochs you want, how many times you want to go through all the data, and you have to tell it how big a batch sizes you want. And you can see this green line, the blue line, it always knows what direction is the best to go, so it's taking it. Well, here the green line is it's kind of more random, right? So every time you can think about it is you're looking at a random subset of the data. So in some ways you're deciding the direction to take based on just a subset of the data. And so it's not a perfect direction, right? It's sort of, you're somewhat doing a random walk, right? In fact, sometimes you might go actually in the wrong direction, right? And the smaller the batches are, right, the more random it feels, right? And in fact, you might even want to have an epoch that have your batch be only one training data, right? So every time you look at one piece of training data and take a little step, right? So you can have really little batches. And so then it would feel like you were taking a random walk. And how do you feel about random walks, right? So this picture is where the purple guy is actually taking a random walk. And so what that means is every time he takes a step, the direction he goes is chosen randomly, except the expected direction is slightly biased to go in the right direction, right? So it's like maybe you're drunk wandering the streets of Toronto, but you can smell home. And so you're stumbling and you take sort of a random walk, but you're slightly more likely to go towards home than not go to home. And one can prove that if you take a random walk that's biased in the right direction, then you will get there just fine. Right? Everybody good with that? Yep. All right, formatting our data.
Just one thing about that last slide.
Right.
Like if you've got sufficient data,
right,
like even way more data than you need,
right,
then you create these batches of data,
right,
and they might be enough as well, right?
Right.
And so then you're not really moving zigzag as much because each batch is as good.
Right.
Is it possible to learn something about your batch as you go along and sort of revise your batch? Like you could kind of watch your path as you travel,
right,
and say, hey, I'm zigzagging a bit. Can I sort of update
try a new batch?
Oh, yeah.
Right, for sure. Well, I will say, all I can say to that is I know that thousands of papers are published in machine learning every day, and somebody has looked at that.
Yeah.
I think it would be hard to come up with the topic to write a paper on that somebody hasn't already done. But yeah, you're right. I mean, that's the kind of game that people play. All right, so let's say we're trying to format our data, right? So suppose I have a particular X value right here. Oh, here's my input, and it has all these various fields, right? That we're going to input here. And maybe a particular field, right, in each of these guys is going to get fed into one of these nodes. And maybe a particular value that gets fed into this node here might be the price of buying something, right? And that's fine. And if suppose the price was this or the price was this, right? It's just one apart. Your machine, right? What does it do? It adds them, it multiplies things, it takes thresholds, right? It's going to treat these two numbers as pretty much the same. And that's okay because these numbers are pretty much the same, right? So that's all perfectly good, right? But suppose the input here is not a price, but the input tells me what street the university is on, and university happens to be on Steele, so that's why I got that, right? So what you're going to be inputting is the name of a street, and you could do that by giving each street some sort of integer name, right? You could call Steele's this name, and you could call Finch this name, and so the different streets have different numbers, right? That's great, but the problem is now here are two numbers that are close to each other, but they have no relative connection between them, right? There's no way, maybe Steele's happens to be close to Finch, but so these numbers are closer, but you can see that that's an awkward meaning. And if you expect your neural net to learn that this number and this number have very different meanings, then that's a lot to ask for your poor neural net, right? And so what you do instead is it's called vectorizing or categorizing, and Google's programs that do neural nets for you have programs that automatically do this for you. All right, so what you're going to do instead of having one node represent street, we're going to have a node for every possible street, right? And when we want it to be Steele's, we're going to set this node to 1, and we're going to set all the other nodes to 0, right? Does that make sense? And this just makes it easier for the neural net, right? It can know what a 1 here means something very different than having a 1 here and a 0 here, right? Does that make sense? Here's another type of processing we want. Here's in this data, maybe this is the data we get from our world, right? This is maybe a person's height, and this is the person's weight. And look at, there's a correlation between their height and their weight. And that makes a valley here, right? It makes a riverbed that's hard to follow along, right? And if we normalize the data, we can turn it from an ellipse into a circle, right? And the way you do that is, we did the whole page on statistics before, right? You subtract the mean, you divide by the standard deviation, and it turns it into circles, right? And why do we do it? As I say here, gradient descent doesn't like these narrow riverbeds. And that made sense to me, all right? But let me tell you another thing that never occurred to me. When this term, I tried to get my second-year students in a completely different course to do some machine learning. And so I had to do it myself. So I got some machine learning programs running, and they were just, I was not getting it to learn anything. And during my very first talk on machine learning with my students, I said, and you need to normalize the data. And at that point, I realized that I hadn't normalized my data. And I normalized the data, and it worked perfectly then. And but what bothered me is that I knew my data wasn't like this to begin with. It was pretty much normal before, right? Instead of being between 0 and 1, maybe it was between 0 and 100 and 0 and 100. But my data was pretty distributed, so I know that wasn't the problem. And so I started asking around people what was going wrong, and my TA told me it had to do with regularization. So remember, when we're trying to regularize, we want to minimize the error and we want to minimize the complexity of the machine. So there's a balance between these two, right? And if I took the same data, but I multiplied all my Y values by 1,000, which effectively what I was doing, then that multiplies by my error by 1,000 squared. And well, that wouldn't be a problem if I'm minimizing things, but it throws off this whole parameter here of balancing it with complexity. And anyway, the truth is I normalized my data and suddenly it worked. And so this is how you normalize data. Any questions about that? I was a little disappointed that Google didn't send me a little note and say, hey buddy, you know, I know I'm not doing very well here, but would you mind normalizing your data? But Google didn't do that. Anybody have any questions? All right, so here's another idea, right? The more data you have, the better your machine learning works. So, but it's hard to collect data, right? Here's one cat, we labeled it as a cat, but we want more data. So what we can do is we can fake it. We can generate more pretend data from this cat. What we're going to do is we're going to shift the cat, right? We're going to take our one data and shift it, and we're going to stretch it, and we're going to rotate it. And what does that do? That just gives us the illusion that we have more data than we really do, right? Does that make sense? The other thing is that there are many parameters that you have to set once you have your data, right? You have to set maybe how many levels in your neural net, right? How many hidden nodes do you want on every level of your neural net? You have to set your batch size, how many epochs to do, right? So there, which measure, which activation levels, right? There are many, many, many parameters. And on my homework assignment, I got them to change all these parameters, right? But, you know, which one do you use? Well, the best thing, sometimes what people do is they just get it to run overnight and they try lots and lots. These are called meta parameters, right? And they try lots of combinations. And just to be a little aware here, suppose you're only trying 3 parameters and each parameter is between 0 and 100, well, suddenly you have a million things to try, right? So you can get parameter blow up pretty fast. But anyway, that's what you do is you try all your data. And then remember before we had training data and we had testing data. And we were telling you never mix the two, because with what you use to train with, you don't want to bring your test data in, or when you're training, you don't want to look at your test data, right? Because you want, when you test it, to be on pure data that you've never looked at before. So now they're recommending you have 3 types of data. You use your training every time you try a different set of parameters, you use the same training data. And then now you have new data that you use just to evaluate which of these parameters do we want, right? You use this training data for every setting of your parameters. And now we have new data, brand new data that you haven't seen before, on which you choose which setting of the parameters do you want. to evaluate them. And then once you've chosen what your parameters are, then we'll have a third set of test data, which will test to see how it works, right? This has to be new, clean data you've never seen before, right? Everybody get that? Here's another idea. These are just lots of quick little ideas, right? Suppose you don't have enough data. Then one thing to do is called k-fold validation, right? So if you have a bunch of data, you're going to randomly choose some of that data to be your test data and the rest to be your training data, right? But if you partitioned it differently, since you have so little data, then you might the answer you get might depend on which part you had. And Martin, this is kind of like what you were saying about evaluating your little batches, right? So here I don't have a lot. This is when I don't have a lot of data. So I'm going to break my data into little pieces. And you have to keep one of the pieces clean to be your test data that you don't use when you're training. So what it's saying is, well, choose one of your pieces to be your test data and train on the other pieces, right? And then do it again, right? Then do it all again where you use this as your test data. No, you use this, the blue is your training data and the green is your test data, right? And you do it in all of these different ways, right? And so in each of these ways, the training data is fresh. It hasn't been contaminated by your training, right? Your test data is clean. And so after you do it all these different ways, then, right, then you have all these different machines that you've learned. And maybe what you can do on your new data is take the average of these machines or something, right? Or you can choose somehow you choose what you want to do with all these machines, right? Does that make sense?
Yeah. And you might want to, like you're talking about spinning your kittens or shifting them around. When you're creating your batches, you might want to have the originals all in one batch and spins in another batch. And
right. Exactly. Good thinking. Right. I saw this somewhere and I don't have much to say about it, but suppose you're learning some function of your X data and you're trying to learn some F, and F is such that if you make a small change in your X, it makes a small change in your Y, and you are trying to you're trying to partition X into K regions, right? You want to say, hey, I got this type of X and this type of X based on this F, right? Then how much training data you're going to need? Well, it seems pretty obvious that you need at least one training example per classification, right? That seems like there's no way to get around that. And what this paragraph in a book was saying was, well, sometimes if you have multiple levels, it can go better, right? Suppose your data are boys, right? And then there's the concept of a boy, but within a boy, there's a face, and within the face, there's an eye, right? So there's sort of a hierarchy of structure. Then somehow it was arguing that you can get 2 to the K regions with only K training data. And that's, actually, now that I say that right now, is this related to what we were doing before? Remember, we were trying to learn our ellipse that had, right? We had the number of pixels was some 2 to the K, right? And so I was trying to learn about all these pixels, but remember, I only had log K training data, right? I only had the number of training data was the log of the number of pixels. So is that related to this? I have no idea. Anyway, this was a paragraph somewhere and I don't know what it means, so let's skip it. All right, so higher dimensions. All right, suppose you're trying to learn and you want to get down here somewhere, right? You want to find the minimum error. But if you're doing hill climbing, the rule is you can never go up, right? So how can you get down here if you can never go up? So what sometimes they do is called assimilated annealing, where they add heat to things. And so at first it's bouncing around with a certain amount of randomness so it can get over these bumps, right? And then they cool it down so it has less randomness, right? So that's certainly one technique. But another technique is you add more dimensions, right? So as soon as you have more dimensions, right, it's easier to walk around obstacles somehow, right? So here you can see in 2 dimensions, it's somehow easier to find the valley. And here's something I grabbed off the internet, right? So these are, what are these balls? We're traveling through 3-dimensional space. And what are the meteorites, right? They're places you can't go to because the air is higher, right? Think about the balls as being high air pockets, and we have to get around the high air pockets to get down into lower air, right? So because in 3 dimensions, it's easier, even easier to move around these bumps, right? Does that make sense? Right, so here, this is one of those rocks that we're trying to, here's a rock that our balls trying to get around this rock. And it's hard to get around this rock, right? And so in 2 dimensions, the rock turns into a hill that we're trying to walk around, right? And in 3 dimensions, the rock turns into a rock that we're trying to get around, right? Right, does that make sense? So having more dimensions can help. But beware, right? So this is just saying there's some evidence of people trying things that if you have more dimensions, then there's more degrees of freedom to walk around, to get around obstacles and find a low valley, right? But the danger is, remember, overfitting, right? If you have more dimensions, your machine is more complex and it might not generalize as well, right? So there's all these various balances to keep track of, right? Does that make sense? And oh, this you've seen already. This is just the more dimensions you have, the more points there are exponentially, right? So here we were talking about reducing the number of dimensions. So this was just an advertisement for the other whole talk. And this is just an advertisement for having not dense layers based on what we did before. Those were just things from, I saw this one paragraph that kind of intrigued me, all right? And so you know, we can drop bombs on a city, and that's a problem. And when you're rebuilding your city from being bombed, right, you want to build it in such a way that it's built so it can withstand bombs, right? If you're anticipating being bombed again in the future, then you want to build your structure so it can handle earthquakes or something, right? In California, you need to build your structures so it handles earthquakes. All right, so what does that mean here? So what they're suggesting, and this seems like such a crazy idea to me, but some graduate student thought of it and wrote their PhD on it, I'm sure, right? What you do is you're going, every time you take a step in your learning, you're going to randomly bomb a subset of your neurons, right? We have a lot of neurons and we just bomb some of them, right? And then with those ones bombed, we see how much error we have, and we take a step in the direction to minimize the error without those nodes in existence, right? And so you took a step, and then you bomb a different subset of them, and you find out how well it does, and you take a step to optimize the parameters with those guys bombed, right? And every step you bomb a subset of your neurons, right? And you might say, why do you do this? And that's a good question. Well, somehow it makes it more robust to change, right? It means that you can bomb a subset of your neurons and it will still work. And why is that interesting? Well, maybe it will be more robust to seeing data that you've never seen before, right? So it seems crazy to me too, but that's all I got on the topic. And but this was a paragraph in a book that said it was useful. People kind of follow that? All right. So we only have a little bit more time left. So this is something we've talked about before, right? You have, what's this one guy doing? It's taking a linear sum of your input and putting it through maybe a threshold, right? And so here we have our weights as our machine. You take a linear sum, and that gives you some Z value, right? And then you either use the Z value or put it through some sort of activation, right? And one thing I told you, and I did this in a co-op term way back when I was a co-op student, is I could hand create. It's kind of like I take my kitty picture and I shift it, right? Before I have this data here, and before I do any learning, I'm going to generate more inputs, right? I'm going to just generate, hey, here's another feature called x1 times x2, and right, I just make as many features here as I want. And then when I'm learning, it's still easy because the purple stuff is all data that's been calculated already. And we just need to find the green weights. And as far as the green weights are concerned, this is just a linear combination of my data items, right? So this learning is still really easy because it's all linear in the features of my data. Does that make sense? All right. And it allows you to get curves that don't look linear. I mean, you're learning the coefficients, so it's linear in terms of the coefficients, but it's non-linear in terms of the original X data. Anyway, so let's call these extra features phi, all right? And somehow we're going to take our original X values and apply phi to them to give us all these extra features, right? And this phi, these features are going to be designed by a human ahead of time, not by the machine learning. All right. This just says once you have the features hand put, finding the weights is easy, just using simple calculus because everything's linear. All right, so it's still kind of linear separator because if we put this through a threshold, then it's a linear separator, right? And now you might have heard of these things called vector machines and support vector machines. And exactly at what point is it a vector machine? I'm not really sure. But let's see what's happening here, right? Here's our training data. And we're going to choose some features ahead of time. This phi, it's going to be, phi is going to take a vector x1 through xn and blow it up to lot more numbers, right? A much bigger vector, right? And then we're going to take, what we're going to try to learn is the weights that minimize the dot product. What our machine is going to do is going to be some weights that we take a linear, we take the sign of these weights multiplied by this much bigger vector, right? Does that make sense? And then we try to learn those weights. So that's kind of what we said before. And as I've said before, what are the weights? Weights are somehow, we ask, given our X value, we take the phi of it, which gives us some really big vector and some much higher our vector space. And we ask, right, what's kind of the angle between the dot product tells you how these two vectors are correlate, right? Anyway, what we're going to now add in this word called support vector machine. And what does that do? Well, suppose this vector, we just have so many dimensions here. We want some really crazy, huge, that given x, computing phi of x could just be too big of a thing to compute, too complicated to compute. So how is it at all useful to us? Well, what we're going to do is let's define a thing called the kernel, right? The kernel is the inside nugget of what we care about, right? We have all our training data. So these are training data pairs. And for every pair of training data, we kind of want to ask how different are these, a distance between this training data and this training data, right? Like a metric space. How far apart are each of my training data pairs? And the way we're going to define it is, suppose you took the first training data and asked for all of its features, and this is a big complex thing, right? And you took the second training data and you asked for all its features, and you ask how do those features correlate, right? How do these two, what's the distance, the correlation between the features, those features, right? Does that make sense? And so let's give it an example here, right? And I had some other examples, but they were way too complicated because I couldn't remember what they were doing. But here's a really simple example. Let x be just one integer. Then, right, so it's just one number. And phi here is going to expand it into lots and lots of numbers. So the way it's going to expand it, it's going to expand it into maybe even an infinitely long vector, right? An infinitely long dimensional space where the first, if the number is x, the first x numbers will be 1 and the infinite rest will be 0, right? It's some definition of a phi, right? It's telling you features of this number x. And that seems like an awfully weird thing to do, right? But when you take the kernel, which is the dot product, if you take the dot product of this and this, what do you get? You get this times this, plus this times this, plus this times this, right? And how far out does it go? Well, as soon as you go past the smaller one, you're going to get all zeros, right? So, and these are all going to be ones up until the smallest one. So what's the dot product? It's the minimum of those two numbers, right? Does that make sense? Now, you might ask, if you wanted minimum, why didn't you just say minimum instead of doing all this weird stuff, right? But here's my best understanding, right? The reason up here the weights are so easy to find is because everything is linear, right? We're in this linear world of everything's linear in terms of the features. And so there are various algorithms that are easy to solve in the linear world. But what is minimum? You may know that minimum is very nonlinear, right? So here we're getting this very nonlinear property out of doing things that feel very linear, right? So that's interesting, if nothing else. And so what do then people do? Well, they have this phi that's too big to compute, but they're able to compute the distance between every pair of training data, right? Just somehow they know it by some other means. They happen to know the answer, right? And then now you're given a brand new brand new value that you want to do something with. And what you need to compute, right, is what you're supposed to do is you're supposed to find the phi of it, right, which is this big scary thing, and take the dot product of it with all these scary weights. And that seems like a big scary thing to do. But it turns out you can simplify the equation to just being the sum of your training data of how far is my new input from each of the training data, right? So if somehow you given a new value, you can ask how far is it from each of my training data, right? Then somehow it works. And so somehow if it's easier to compute the kernel than it is to compute the phi, then this is a useful method. Now, the problem is, in order to do this, you have to compare your new value to everybody in the training data, right? And that takes a lot of time. So this is where the support vector machine comes in, right? So given all your training data, there's some algorithm which will say, well, I don't need all of this training data to support what I'm trying to do. I can just have a small subset of my training data to be my support vectors, right? And then when I have a new value, a new vector X here that I want to deal with, all I have to do is to find out how far in terms of the kernel, how far I am from each of the support vectors. And that will give me the answer, right? Does that make sense? And if you're understanding what I'm saying, then that's all I got, because that's all I know. But I know that this is, I've heard the term support vector machines all over the place. And so I figured I should learn at least this much about it. Right? Does that make sense? And I have this weird example, but I don't think we should do it. If you want to play with this weird example, is the input has to be compressed down from 8 down to 3, and basically you can teach it to learn binary, and that's kind of cool. And that's all I've got to say. Any questions about anything?
No questions.
No questions? Daniel sometimes have questions. Martin sometimes have questions.
John, I do have a question.
Yeah.
Did I understand how we can spot the machine can spot the cat, can spot the dog, and tell us if it's a cat, dog, bike, so forth. How does it tell us where in the picture that cat, that dog, that bike actually is? In other words, the pixel bounding box. How would it do that?
Right. Well, that's a very good question. And if we're using a convolution net that's learning is there a cat somewhere, then in the end it won't know where the cat is.
Right.
So, but my belief is that if you had your neural net that came through and then said cat, and then you went backwards through your neural net, right? At some point it's taking maxes and it's doing these other funny layers where it's convoluting at the various places. And if you went backwards and said, why did you tell me this was a cat? And you went backwards, and it could probably narrow it down. I said it was a cat because these features were highlighted down here in this area of the image. I bet you could work backwards and determine where your cat was.
Okay. Then building on that question, where does the transition occur from a machine learning environment to some sort of a programmatic if-then type of environment for autonomous vehicle navigation, for example? In other words, it spotted all the signs, the street signs, the curb, it's found the cat, it's found the bike. Where does it then, how does that then come into a program?
Yeah, I've had the exact same question, right? Because if you're Google, you want at some point to say, if you see a stop sign, stop, right? And then you need to be able to set, you need to put in some if statements. Right?
Yes, correct, right.
And you want to be able to modify the program to say, oh, now you've gone to Europe, so, or maybe you've gone to India, so you can completely ignore red lights, right? So you need to be able to put these if statements in, and I have absolutely no idea the answer to your question.
Okay, no problem. Maybe that's level 2 of this class.
That's level 2 taught by somebody else. You literally have heard everything I know about machine learning now.
I thought there was one more lesson.
Oh, there's one more. What are we doing in the last session is I have various images of things that machine learning has done, and I don't have any answers. We'll just open the floor to people talking about, are they good or are they evil?
Okay.
Are they going to make the world a better place or a worse place? And I don't have any answers to those questions. So don't come to that one hoping for me to give you answers. I'll give you some cool examples, and then you'll have to decide for yourself whether the world's going to be a better place or a worse place in the future. You know, and what are the various highlights? How do you deal with racism? How do you deal with unemployment? How do you deal with distribution of wealth, right? How do you deal with privacy? How do you deal with I don't know, all of these things, right?
Yeah.
Any last questions? Is everybody good?
Yeah.
Good. Somehow, you know, I never have timed my talks, but they've all somehow just been an hour and a half. All right.
It's good. Thanks.
Okay. Thanks, everybody. Have a good. Thanks for the heart, Daniel. We'll see you all next week, and then we'll be done. And if anytime anybody wants to talk to me, you know how to find me. And if anybody wants to watch the videos, they're all going to be posted as I get them. So I will say goodbye to everybody.
Thank you.
Thank
Bye,
you.
everybody.
Evening.
Bye.